Alright, so we have this question here that says, prove by induction that the sum of the first n even terms is equal to n plus 1 here. So now, first things first, we need to understand what this term means here, even. So a number is said to be even if it is divisible by 2 and it doesn't leave a remainder there. So meaning that there, if we assume to say, let's get natural numbers, so for example we have 1, 2, 3, 4, and so on and so forth here. How do we convert these to even terms? If we multiply this 1 by 2, we're going to get a 2 here. If we multiply this 2 by 2, we're going to get a 4. If we multiply this, we're going to get a 4 here. If we multiply this 3 by 2, we're going to get a 6. If we multiply this 4 by 2, we're going to get 8 here. So meaning that here, when we get these natural numbers up to n here, meaning that the nth term here is going to be 2 multiplied by n like this here. So meaning that here we're going to have this statement that we're going to work with, which is 2 plus 4 plus 6 plus 8 plus 2n is simply equal to n open brackets n plus 1 like this here. So now, case number 1 under mathematical induction is that we need to show that the statement is true for n equals to 1 here. So we need to show that the statement is true for n equals to 1 here. So what we just simply do here is we get this expression on the left hand side that has n, we equate it to what we have on the right hand side here. So meaning that here we're going to have 2n is equal to n open brackets n plus 1 like this here. Then what is n here, we substitute with this 1. So we're going to have 2 multiplied by 1 equal to 1 open brackets 1 plus 1 here. Then 2 by 1, we're going to get a 2 equal to, this is a 1, so 1 plus 1 here we get 2, 2 by 1 here we get a 2 as well. So therefore, the statement that we have here is true for n equals to 1. Okay, so we go to step number 2 now, so which is we can call it case 2 or step 2. So I'm going to use step 2 here. So this step we call it the inductive hypothesis. So under the inductive hypothesis here, we make an assumption that the statement that we have is true for n equals to k. So meaning that here, if this is the inductive hypothesis and we say that the statement is true for n equals to k, then we copy the statement the way it is here on top. Then where there's n, we just substitute with a k. So we're going to have 2 plus 4 plus 6 plus 8 plus 2k equal to k open brackets k plus 1 like this. Okay, then we go to step 3. So step number 3, we need to show that it's true for k plus 1, n equals to k plus 1 here. So here we need to show that this is true for n equals to k plus 1 here. Now, when you talk of this n equals to k plus 1, it simply means that we're adding a new term to the already existing terms that we have here. So I mean that we're moving a step further from the kth term, then the next term becomes the k plus 1th term there. So meaning that here, okay, so let me just do this. Alright, sorry about that. Okay, so meaning that here, we're going to write this statement the way it is here. So we have 2 plus 4 plus 6 plus 8 plus 2k, then plus now, since we're moving a step further, which is the k plus 1 term here, so we're going to say plus 2 open brackets k plus 1 equal to, even on the right hand side of the statement that we're working with, where there's n, we substitute with k plus 1, so we're going to have k plus 1 open brackets k plus 1 plus 1 like this here. Then now, if you look at these terms here, starting from the first term here, all the way up to the kth term, these here, they give you the inductive hypothesis. They give you the left hand side of the inductive hypothesis there. So meaning that, where there are these terms here, we can just substitute with what we have on the right hand side of the inductive hypothesis there. So meaning that here, we're going to have k, open brackets, k plus 1 plus, this is going to be 2k, so 2 by 1 they are going to get plus 2 equal to, then this side we're going to have k plus 1 equal to k plus 2 like this here. Now, we can just try and expand what we have this side here. So if we expand what we have this side here, we're going to have k squared plus k plus 2k plus 2. Let's also try to expand what we have on the right hand side. We check if we're going to have the same thing. So k times k, there we get k squared, k times 2 we get plus 2k, 1 times k we get plus k, then 1 times 2 here we get plus 2 like this here. So therefore here we're going to have k squared plus 3k plus 2 is equal to k squared plus 3k plus 2 like this here. So therefore we have that the left hand side is equal to the right hand side here. So now if this is the case here, then we just say the statement that we have is true for n equals to k plus 1. So here we're going to say therefore the statement that we have here is true for n equals to k plus 1. So if this is true for n equals to k plus 1, then we say by induction, so we can just simply say by induction the sum of n even numbers so let's say integers is equal to n plus like this here. Alright, thank you. Let's look at the next question there.